So now we have already learned how to do acid catalyzed dehydration in even reactions. We will do some applications of that mechanism. Now one of the very important application of it is Pinacol Pinacolone rearrangement. What happens in Pinacol Pinacolone rearrangement? A diol gets converted into a ketone in the presence of H2SO4. So dehydration takes place and this diol gets converted into ketone. Now we are specifically talking about Pinacol or Pinacol type diols, which are vicinal diols. Let me just show you what is Pinacol. So Pinacol is, this is my Pinacol. This is my Pinacol. Okay, so this is a diol, right? This is a vicinal diol, and when this will get converted into this type of ketone by removal of water in the presence of concentrated H2SO4, this process is called as Pinacol Pinacolone rearrangement. So we are not going to talk about only this compound, but more compounds similar to this structure. Okay, this particular ketone is called as Pinacolone. Okay, before even I start Pinacolone rearrangement, I'll explain you how Pinacol forms first, so that just in case if you get a starting material in any reaction and they give you the conditions of preparation of Pinacol, you should be able to identify and form the Pinacol and then do the rearrangement. So how the Pinacol formation happens? What we take is, in the normal lab scenario, we take acetone. Okay, now we treat it with Mg in the presence of Hg and water. So basically we put Mg first and then we put water. We don't put both of them together, otherwise Mg will react with water and will form its respective hydroxide. So what happens, this species, these two ketones, in the presence of magnesium, oxygens of both pull their electron density and basically forms the species like this. Okay, and parallelly Mg loses its 2 electrons and form Mg2 plus. Okay, now there will be a reaction between this species and this species. So basically this and this both will react together in such a way that OMg and this will form and the carbocation will stay over here. Now the 2 electrons which have been released by magnesium, those 2 electrons, out of these 2 electrons, 1 electron will go to this carbon and another electron will go to this carbon, forming a radical. So this will get converted into OMgO, a radical over here and a radical over here. These two radicals will combine, and will form a bond forming this. Okay, so what we have done, we have taken these acetone. Acetone, in the presence of magnesium, this magnesium will try to form the bond with oxygen, and parallelly this oxygen will break its bond with carbon, getting a negative charge or positive charge over here, or you can call it, that will be a, I have just shown you the structures in the proper negative and positive charges, but it may happen simultaneously, so you may not be able to see this negative charge at all. So O will receive delta negative, or will start becoming negative, and Mg will attack on it by losing its electron. Mg will be in Mg2 plus state, so two species will get attached like this, and other two carbons will have a carbocation formed on it. Now the two electrons lost by magnesium, one electron will go to this carbon and one electron will go to the other carbon, forming the radical over here. Next step, the radicals will combine and will form a bond between one carbon and the another carbon. Now as we have got, so this is my first thing. Now in second, when we have already got this, now in the second step, water will attack on this magnesium, and then magnesium will form MgOH whole twice, along with the removal of H plus and H plus. That H plus, the H plus will come out from water. One H plus will go and attach with one oxygen. Another H plus will attack and go to the another oxygen. This Mg will come out and will form MgOH whole twice, and hence resulting into OH and OH. Is this clear? So what has happened? This water will form the bond with magnesium to form MgOH2, and two hydrogens will get released, and those two hydrogens will attack on each oxygen to form OH and OH, and that's how we will get this vicinal diol. You don't have to mug up the whole mechanism of preparation of Pinacol, but you should know this. This is the starting material, these are the reagents, and this is how the Pinacol will be formed. Now I'll show you how the mechanism of this reaction works. Okay, you can just note this down and then I'll rub it off. Now let me explain you the mechanism of Pinacol Pinacolone rearrangement. Now understand, now focus and try to relate it with other mechanism what we have learned in E1, that is dehydration of alcohol. So what we do over here is, this is my starting material. Now as we already know that H2SO4 is present over here, hence we will get H plus to attack on. So this H plus will attack on either of the oxygens of the alcohols present here. Here this particular compound is symmetric, so it really doesn't matter where H plus will go. So let's say H plus goes over here and forms a protonated alcohol. So the intermediate will be formed as, this will be the protonated alcohol. So this is my protonated alcohol. Now this protonated alcohol will break its bond, this OH2 plus will break its bond with carbon, leading to the formation of a carbocation over here. So I will get and CH3 over here. So this is the carbocation I have got. This is my carbocation intermediate. Okay, now we will see if we can do any rearrangement to make it a stable carbocation. So carbocation will form and carbocation will go for a better stability if there is a possibility of any such scenario. So now look at the neighboring carbon. We have an OH present over here, which will give the mesomeric stability to the plus charge if plus charge shifts over there. So we have already discussed this, that a carbocation will do anything to get plus M stability. So there will be a methyl shift happen over here. This CH3 will shift over here and this plus charge will shift over here. So what will happen? 1,2 methyl shift will take place to give plus M stability to our carbocation, and this will become OH plus CH3, 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 CH3. So this will be my structure form. Now this oxygen will try to, due to its mesomeric effect, it will try to make a bond with this carbon, right? And this pair of electron will try to form a bond with the carbon, leading to the formation of a double bond, and oxygen will gain a positive charge over it. Due to its positive charge, it will try to break the bond with hydrogen. Eventually hydrogen will get released and a double bond oxygen will be formed. Let's see. Let me write it down over here. So how will it look like? It will be CH3C, double bond oxygen, hydrogen, and one pair of electron and plus charge. This is how it will look like. Now the bond between oxygen and hydrogen will break. Hydrogen will get released. So removal of H plus will take place, and this will become CH3C double bond O, C, CH3, 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 and hence the formation of Pinacolone take place. So why do we call this reaction as an acid catalyzed reaction? Because we took acid in the beginning, H plus was the one which was starting the whole reaction, and at the end of the reaction we got the H plus back. So H2SO4 didn't participate in the reaction, as in like didn't form any product as such, or any H2SO4 part is not involved in the compound formation. Instead, H plus was initially introduced to start the reaction. Once the product is formed, we have got the H plus back. This is our Pinacol, Pinacolone rearrangement. Now, there are many variations to this particular form of a molecule. So, many diols will tend to do the similar kind of mechanism. Now, this is the one which we started first, or you can say which was introduced first, and now after this many other diols do the same reaction. So it's not necessary that when we say Pinacol, Pinacolone rearrangement, you will always get this molecule. You may get some other molecule similar to this, and you have to do the same mechanism to get similar kind of ketone. Now one more thing what you have to remember is we have already spoken about the migratory aptitude of the species to when the carbocation forms. To get the more stability, there are shifts which happen: hydride shift, methyl shift, phenyl shift. So so migratory aptitude, which I had mentioned in the class, I told you that is not mostly followed by in most of the reactions, because in most of the cases when migration happened, that step is fast. But here migration of CH3 or migration of a species to stabilize the carbon is a slow step, and hence migratory aptitude will be strictly followed. Okay, so this is one of those cases where migratory aptitude is strictly followed. And so here we have CH3s, but we may have different other species over here, and that time you have to be very careful while shifting one species from one position to another to make the carbocation stable or to do the carbocation rearrangement. Now we'll see the next example. Now let's see the next example. Let's say I have this diol. Instead of both the CH3s, I have put a benzene ring over here. Now if I react it with H2SO4 and heat is required for elimination, make sure this is a concentrated H2SO4. You are not taking dilute one, because dilute H2SO4 job is to hydrate the molecule, not dehydrate. So now what will happen? H plus will attack either of the two OH over here. So which OH will it choose to attack on? Wherever we can form a better stable carbocation. So if the carbocation form on this carbon, it will get resonance stability from this benzene ring. So hydrogen will attack over here. So H plus will attack on this, will form a protonated alcohol. This will form a protonated alcohol, and then this OH plus will get removed, forming carbocation over here. This carbocation has got a resonance stability from the benzene ring. Now, as we have already discussed, that this plus charge will go to the place where OH is present, so that it can get the mesomeric stability or plus M stability of that OH and can form ketone later on. So this plus charge will shift over here and CH3 will shift over here. So 1, 2 methyl shift will take place. So next is 1, 2 methyl shift. So this will become CH3, CH3, benzene, OH plus and CH3. Okay. Now this oxygen will try to form a bond over here with the carbon. Okay, and due to its mesomeric effect, and will lose this hydrogen as H plus, and hence eventually we will get minus H plus and we will get a ketone. C double bond O CH3. So this will be the ketone formed after rearrangement. Is this clear? What two things you have to keep in mind? First of all, the carbocation will form only in that location where it is getting the better stability. So that carbocation should be the whichever place we are getting the stable carbocation, there the carbocation will be formed. Then the shift will happen from the other carbon, so that plus charge can go to the other carbon to get plus M stability of OH, and that migration of the group will happen according to the migratory aptitude, which we had already discussed when we were talking about the carbocation rearrangement. Okay, so this is then another example. Let's see the third example for the same. Now what if I put benzene over here instead of CH3. So now it is symmetric from both the ends. So now let's see how it will impact the reaction and what will be the product formed. Again, the first step will remain same, that H plus will form a protonated alcohol. So it can go either this hydrogen OH, or it can go to either this OH or it can go to this OH. Either the way it can go, and it will form a protonated alcohol. It won't affect the whole system. So the protonated alcohol will look like this: OH2 plus, CH3, pH, OH, CH3 and pH. Okay. Now removal of this water will take place, and a carbocation will be formed: CH3C plus, pH, COH, CH3 and pH. Now when the migration of a species has to happen, so that this plus can go to the adjacent carbon, you have to be really careful. What we have to understand over here is, we have two scenarios over here. Okay, one is this plus shifts over here and CH3 moves over the other carbon, or in the other case benzene moves on the other carbon. Let's see what difference will it make. According to the migratory aptitude anyways, the benzene should shift to the carbon. Okay, but we will understand the reason why it will shift. So we have let's say CH3 has shifted when methyl shift has happened. Methyl shift. What will be how the carbocation will look like? It will look like this. This is how my carbocation look like. And when phenyl shift is happening, my molecule will look like this. Now, what is going to be the next step? Next step is the removal of hydrogen due to the mesomeric effect and the bond formation between oxygen and carbon. Now look at this scenario where CH3 has shifted and benzene is still present here. This positive charge will get stabilized due to resonance in benzene. So basically the plus charge magnitude of plus charge is going to reduce. Why it is going to reduce? Because this plus charge will not be localized to this carbon. Instead, it'll move to the benzene chain, it'll do resonance over there. So the overall plus charge is very less, and hence this will not be able to attract the pair of electron of oxygen toward itself and will not be able to make the double bond effectively. Whereas in this case, this plus charge is localized to the carbon itself, and hence will be pulling these electrons toward itself to form a double bond, and the release of H plus will be easier and the formation of ketone will be easier. Let me just explain this again to you. What is happening in this case? This plus charge is a localized plus charge because it will move to benzene, will do the resonance, and hence this plus charge is, the magnitude of this plus charge is not strong enough to pull this electron density toward itself, form a pi bond and kick out the hydrogen. Whereas in this case, this plus charge is quite localized. It will attract this pair of electron toward itself to form a pi bond and will release H plus. So formation of ketone will be easier in this scenario as compared to this scenario. So the reaction will not proceed in this manner but will proceed in this manner. So basically phenyl will shift over here and plus charge will shift over here, which justifies your migratory aptitude order also. In migratory aptitude order also, phenyl shift happens the first, okay, and methyl happens later on. So basically phenyl shift is faster than your, or phenyl shift is more favorable than your methyl shift. So it will form CH3, C, CH3, PH. Oh, did I do? Yeah, so I think by mistake I have written CH3 over here. It is not CH3, it is phenyl over here. So this is also phenyl, single bond, double bond oxygen and CH3. So here phenyl shift will happen instead of methyl shift. So methyl shift will not take place. This you have to understand really properly. So that means any species which is present on the adjacent carbon which can reduce the magnitude of plus charge has to shift on the adjacent carbon, and plus charge will shift on this carbon to get the plus M stability, or to get or do the mesomeric process with OH and form ketone. So anything which can reduce the magnitude of plus charge will get shifted, and plus charge will shift on the other side forming a ketone. Okay. Now I'll give you a few questions. Try them on your own and then we will discuss the answers. All of those questions are using these concepts as an application. Try it out and then we will discuss.